All right, so you guys all should have a worksheet that looks like this. All right, so what I'm going to do is I'm going to go over the equations for this unit, and I'm going to be quite honest. These look disgusting and complicated and awful. The equations, once I go over them, you're going to realize are not that bad. The hardest part is actually just typing it in a calculator. So you know how sometimes I'm like, no, I want every person at your table to type it in? This is one of those again. So it is incredibly important that each and every one of you, as we do these practice problems and go through it, that each of you are typing into your own calculator the equation. Some of your phones, if you're using your phone as a calculator, is not going to work well. So as a heads up, the pink calculators work really well. And so you're going to want to use one of those if you have one available to you. If you're having any issues with your fancy pocket calculator, you'll want to grab one of my calculators because it'll just make it a lot easier. All right, so first things first, I'm going to go over the two equations. And so I'm going to kind of zoom in on each of these, and then we're going to go from there. So on your paper, you guys are going to take notes as well. This FG is gravitational force. And this is going to be the gravitational force between any two objects. This could be the gravitational force between the moon and the Earth. It could be the gravitational force between the Earth and the sun. It could be the gravitational force between me and my computer. Especially this time of year, Valentine's Day is just around the corner. You can also calculate the gravitational pull between you and your significant other. Because you both have mass, so everyone is attracted to anyone else. So there you go. You can calculate just how attractive they are. This G. This G is the universal gravitational constant. The universal gravitational constant is going to be the same for everything. And just like G was always the same on Earth, this big G is always going to be the same for everything. Hence why it's called the universal gravitational constant. And this G, this capital G, is equal to 6.67 times 10 to the negative 11th. And then there's some crazy funky units after it, but I don't want you to get lost in the units. The units are disgusting. So I'm going to have you guys focus that it's 6.67 times 10 to the negative 11th. I wish. No, it has to be negative. I know. Okay, and then M1 and M2. These are the masses of the two objects. So if I was doing the gravitational attraction between myself and my laptop, I would use the mass of my laptop and the mass of me. If I wanted to know how much I was attracted to my phone, I could do the mass of me and the mass of my phone. So it doesn't matter what it is, you just use the mass of the two things. Now, 3 times 2 is the same thing as 2 times 3. I say that because it does not matter which order you put in the numbers when you go to calculate it. Because I could do 3 times 2 or I could do 2 times 3. I'm still going to get 6. And so it does not matter which one is M1 and which one is M2. And then we get to this R squared. All right, so before we get there, I want to show you a couple things. We're going to have a sun. Here's my sun. And I'm going to have a planet going around the sun. They go in a circle. Circle-ish. Okay. Kind of exactly a circle. When I draw it on my whiteboard, like over there, they are not pretty circles. They're kind of circles. Okay, so there's a planet. And if I wanted to know the attraction between my sun and the planet, I would need to know the distance from the center of, the center of my planet to the center of my sun. Okay, so that's that distance. All right, if I wanted instead, let's say I have an atom. All right, and in an atom, there are neutrons, and there are protons in the nucleus. And then there are these really fun things called electrons. And the electrons go zooming around the outside. And basically, whenever you do anything with electrons, you don't care about the electrons on the inside. You only care about the electrons on the outside. So let's say I have an electron over here. I don't know, let's say it's like that. And I want to know about the attraction between this electron and my nucleus. And so then I would need to go from my electron to the nucleus if I wanted to talk about how far they were away from each other. All right. Let's see. I could also talk about, I know, on Earth. I'm standing on Earth. Okay, here's the Earth. And let's see. We're going to put some super awesome continents on here. Okay, there we go. Continent. Okay. All right, perfect. All right, so there's some continents on my Earth. There. And I'm going to have a person standing on it. We're going to put the person right here on the edge of the Earth. Whoa. Here's my person. They're standing on the Earth. And I want to be able to talk about how far it is from the center of my person to the center of the Earth. So center of the Earth to the center of my person. If you're thinking geometry, what did I just draw? The radius. Right? Do we all agree? The center of one of these things to the center of the other in all of these cases is the radius. Yes. Okay. That is why when we talk about the distance, let's say I wanted to now do the distance between me and my laptop, because, I practically live on my laptop these days. I would also use this distance. So the center of me to the center of my laptop. And so because most of the time it is the radius of the circle, I'm going to just keep using R. Because most of the time that's what it is. Does that make sense? Why it's an R in the equation? Yes? Good? Okay. Cool. All right. So that's what this R is. This R is the distance from the center of one to the center of the other. The distance And now I'm going to compare it to this one. So this one is electrostatic force. And one thing I would like you to notice is just how similar these two equations are. And this r squared is the same thing. This is still also the distance between the two things that we're looking at. For the first one, when we were talking about gravitational force, we're looking at the force between two masses. And that's why we have these masses here. For this equation now, we're going to look at the force between two charges. So when you think electrostatics, you're going to think like positives and negatives, and are they attracting or are they repelling, and how strongly are they attracting or repelling one another. The K, instead of having a universal gravitational constant, this K is actually called Coulomb's constant. And Coulomb's constant is always going to be 9 times 10 to the 9th. And I know K and C are not the same thing, but they sound similar, so we'll just go with it. So that's Coulomb's constant. And it will always be 9 times 10 to the 9th. And then these Q's, these are my charges. I know that doesn't make a ton of sense, but we're just going to go with it. So these are charge 1 and charge 2. So the charges. Again, it does not matter at all what order you do them in. Not at all. All right, any questions so far? Good? Cool. All right, so let's do an example. So the first thing that we need to do is we need to identify which of the two equations that we're going to need to use. So I'm going to speak very quickly about this. And this should not be terribly difficult. Okay, if I wanted to find the force between two things that have mass, which equation do I use? The one on the left or the one on the right? This one. Yeah, good. The gravitational force one, because that's the one between two masses. Which equation do I use if I want to find the force between two charges? The one on the right. If I ask you to calculate electrostatic force, which one do you use? The one on the right. This is your electrostatic force equation. Which one do I use if I want you to calculate gravitational force? The left. Okay. Now, one thing I want to point out in addition to this is I need to think about, okay, there are two different constants. And one of the common mistakes that students make is they use the wrong one. Okay, if I'm doing electrostatic force, which constant do I need to use? Which one? Yeah, I have to use this one because that's the one that belongs over there. And if I'm doing gravitational force, then I have to use my universal gravitational constant. These two numbers are not the same. You're all looking at me like right now like, duh. If I don't say anything, then students always use the wrong ones and they don't pay attention to which constant they need to use. So just be careful. Now that I've said it, you're going to be like, duh, of course you have to use the right constant for the right equation. And that's great. Then nobody makes that mistake. And we're good. All right, so number 2 says an astronaut is 6,941,000 meters away from the center of the Earth. The Earth has a mass of 5.97 times 10 to the 24th kilograms, and she has a mass of 70 kilograms. What is the gravitational force acting on the astronaut? All right, which equation do I use? The first one or the second one? First one. All right, so I'm going to rewrite this equation. You guys don't have to, but when I explain it, it tends to help students if I've written it out. All right. So all I need to do is plug in the numbers. Now, I am going to require that you write this next part. So this part is optional. And then this part is going to be required. So I want you to write FG equals, and then I want you to write all the numbers in. What is capital G? There's no G in the problem. What do I do? What do I do? Oh, yeah, I have to use this thing. All right, so G is 6.67 times 10 to the negative 11th. All right, good. All right, and then I'm given two masses. I'm given a mass of 70 kilograms and a mass of, a mass of 5.97 times 10 to the 24th. Which one is M1? It does not matter. Good. I just get to pick one of them. So I'm going to do 70 first. And I'm going to do 5.97 times 10 to the 24th. Divided by. All right. R squared. So I have to find a distance. Oh, there's my distance. 6,941,000 meters. All right, what's wrong? What did I do wrong? Oh, I need to square it. Okay, now here's my recommendation. And I'm going to tell you what the common mistake is for number 3, and then I'm going to have you guys work through some of these. The hardest part, and I'm not joking, the hardest part about this unit is typing it in your calculator. I know I said that once, I'm saying it again to emphasize. When you go to square this, okay, and let's say I just square this number. I will get 4.81 times 10 to the 13th. Ooh, this is something else I need to show you guys real quick. Okay, in my calculator right now, it looks like this. It says 4.8177, blah, 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 blah. E13. That E means times 10 to the. So this E is the same as 4.8177 times 10 to the 13. So E is this part. And sometimes in your calculator, it'll have a little plus here because this is a positive 13th. And if it was a negative 13th, then it would have a little negative there. Got it? Oh, you'll be fine. You'll be fine. All right, so here's the issue, is that if I type this into my calculator and I get some number here divided by, I have to put parentheses around this 4.81 times 10 to the 13th. If I do not put parentheses around it, what your calculator is going to do is this instead. Your calculator will go blah, 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 and it says divided by 4.81 times 10 to the 13th. If you don't put the parentheses around it, this is the same as blah, blah, blah divided by 4.81 times 10 to the 13th. Do you see the problem? Okay. With the parentheses, if I go blah, 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 divided by, and then I put parentheses in, then this will be equal to blah, 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 divided by 4.81 times 10 to the 13th. Does that make sense? Okay, so be really careful, and if in doubt, put in extra parentheses. If you're trying to figure out how to put this into my calculators, and you're using the pink calculators, I will type in 4.81 just like normal times, and then I need to do 10, and then there's a button that looks like this. It's called a caret. And then I type 13, and so that's the same as times 10 to the 13th. If you're using my calculators and you need a negative number, let's just say you're doing times 10 to the negative 11, then if I'm doing 6.67 times 10, there's a button. Oh, I have to do to the. And then there's a negative button. You cannot use the minus button. You have to use the negative. And the negative looks like this. It's next to the decimal point. And then I can do this. And so that's the same as 6.67 times 10 to the negative 11th. Are we good? I mean, now we just got to do it, right? It's a lot of nasty numbers. That's exactly what it is. And then once you get down, oh, I don't want to overwhelm you. Can I tell you one last thing? Okay, when you get down to like number 4 or something, what number is it? Yeah, number 4. On number 4. What? This is called a mu. Okay. Or you could call it a micro. And so 4 microcoulombs is the same as 4 times 10 to the negative 6 coulombs. Because I'm teaching you real world physics. That's why. So I'm using real numbers instead of pretty fake ones. Oh, I know. Real world is obnoxious. All right. Are we good? Okay. The answer you should get for number 2. Are you guys ready? I'll just write it down on here. I'll show I'll move it up so you guys can see the equations again and the notes if you're trying to figure stuff out. Because I want you to know if you're getting the right answers, because the hardest part is typing it into the calculator. Okay. So number 2, you should get 578.57. And number 3, you should get 1.98 times 10 to the 20th. All right. Ready, set, go. I'm going to come around and help you guys.